particular PowerPoint presentation is going to be on sample size. One of the probably most appropriate and common questions that's asked is, how much data do I need to collect? So before we run out and collect data to do a t-test or a proportion test or a two-sample or paired or anything like that, question is, how much data do we need to collect? Because if we don't collect enough, and then we can't make a good decision because we don't have enough data, that's a problem. And of course, we don't want to collect too much data if we only need a certain amount. We don't want to collect way more than that and waste resources and time and money collecting that data if it wasn't necessary to take that much data. So both sides are important. We'll look at this for means and proportions. The most common way to find sample size is to use the concept of power. Now, power refers to the probability that we reject the null hypothesis when the null hypothesis is true. So let's suppose that you're looking at a one-sample mean test, and the null hypothesis that you're on target, and the alternative hypothesis that you've shifted. So power of the hypothesis test refers to the probability that you reject the null hypothesis when you have shifted. So it's basically when you've shifted, it's the probability you correctly say, yes, we have a shift. So it's the probability of correctly identifying the shift when it occurs of a certain size. Okay? So that's what the power of a test is. If we write it out a little bit more mathematically, we can say it's probability you reject H0. Vertical line there is representing given or assuming. So assuming or given that the alternative hypothesis is true. So given you shifted, it's a probability you reject the null hypothesis and say you have a shift. So we can look at our usual two-way table that describes all our decisions and possibilities from a hypothesis test. So the rows represent the decision from a hypothesis test. Either we reject the null hypothesis or we fail to reject. Just example using the p-value. So if the p-value is small, we're going to reject the null hypothesis. If the p-value is big, we fail to reject. Now the columns represent something we'd never know, but in reality, either H0 is true, we're on target, or H1 is true, we've shifted. So these represent the four possible scenarios. So let's look at the first line there, reject H0 line. If I reject H0 when H0 is true, then I've made a mistake. It means there was no shift, but I collected data and said there's a shift. So we call that a type 1 error, commonly referred to as alpha. Now the next one over is if HA is true and I reject the null hypothesis. Well, that's the right thing to do. It means you have shifted and you say you've shifted, and that's what we refer to as power. Now, the bottom line, if I fail to reject when the null is true, well, then I made the right decision. It means we have not shifted, and I say we haven't shifted, so therefore, I made a correct decision. And the last box in the lower right there, if I fail to reject when the alternative is true, right, then I've made a type 2 error, okay? So basically, I've missed, we shifted, but I missed it, and we refer to that as beta or a type 2 error. So if we write that out as a type 2 error, we could say it's a probability I failed to reject H0, given that HA is correct, and you could see that that would be 1 minus power. Okay? So by finding or specifying a certain power level, we actually will find the probability of a type 2 error, or the beta value. Okay? All right, so that's what's going on in this power idea of what we're trying to get at. So we're fixing power at a certain size, given that we made a certain shift. Now, you've got to keep in mind that because of what's going on, that we do need to be careful that it's for a given shift. And we'll come back to that. If we're going to calculate power, we need 4 things in general. The first is the significance level. We have to know, are you using 0.05, are you using 10%, are you using 1%, what are you using? That you'll see directly where that comes into the equations for calculating power and thus the sample size. So that's an important question. We need to know the specific alternative hypothesis. Now by that we mean Are you doing greater than, less than, or not equal to? So we need to know, are you only looking on the right-hand side, only looking on the left, or are you looking on both sides? Okay, that will also impact the analysis. The specific alternative value you wish to detect. Okay, so a specific value in the alternative. So if I'm doing a greater than, I need a specific value in there. The reason is that, remember that power is calculated assuming the alternative is true. Well, let's go back to our example. The null hypothesis were on target, the alternative hypothesis that we shifted. Well, we know, when we assume H0 is true, we know what we're talking about. We're talking about on target, whatever that value is. But when we say the alternative is true, that's basically any value in some big interval that does not include the target. Okay? So unless I specify a specific value in there, then there's no way to calculate that because I don't know where HA is true. It's true in an interval, so it's impossible to calculate. So we need to pick a specific shift value and then calculate it there. Finally, we will need to know the standard deviation. That will play a role within the calculations because when you define that shift in step 3, we need to know how far out that shift is, so we need to have an idea of the general shape or variation to the curve, so we will need to know that. We will show later that there is a way around number 4 if we do not know the standard deviation, but the standard way of calculating it is to assume we know it. Consider a one-sided hypothesis test for the population mean when the standard deviation is known. So in particular, we're going to look at a greater than test, okay, and we're going to assume that we know the standard deviation to start with. Okay, so we know sigma, we're doing a greater than test. So we know that we reject the null hypothesis with a greater than test, right, a z-test, when z equal to y bar minus mu0 over sigma over squared n. That's our test statistic. If that is bigger than some z alpha, because I'm doing a greater than, right, so I don't need to divide by 2 or anything, that's bigger than some critical value z alpha, then I reject the null hypothesis. So remember, that's part of our equation. What is rejecting the null hypothesis? So let's suppose we're concerned if the mean shifts to mu1, where mu1 is bigger than mu0, meaning it's in our critical region. It's in the alternative hypothesis. Okay? And we can write power as the probability. Now, the left-hand side of the vertical bar is the rejection part, z bigger than z alpha. Okay? Given that the alternative is true instead of the null. So instead of mu equal mu0, it's mu equal mu1. Okay, so that's where the alternative being true is on the right-hand side of the vertical bar. The left-hand side is the reject H0 part. Okay, so under HA, though, if the alternative is really true, and it's mu is equal to mu1, then y bar minus mu0 over sigma over squared n, what we're calling z in general, does not really follow the standard normal or z distribution, because under the alternative, y bar is actually centered at mu1. So therefore, y bar minus mu1 over sigma over squared n will follow a z distribution. So we got to re-standardize our y bar. So we start with the same equation from the previous slide. And basically, I need to isolate y bar and then re-standardize it using mu1 instead of mu0. So to do that, I simply move sigma over square root n to the right-hand side of the inequality. Sigma and n are both positive, so we can simply move it over without any worry. Then I need to move mu0 over to the right-hand side. So I simply add mu0 to both sides of the inequality. So now I have y bar bigger than mu0 plus d alpha sigma over squared n, given the alternative is true, which again is mu at mu1. So now what I need to do is re-standardize that so that I have a... So under HA, y bar has a mean of mu1 and the standard error of sigma over squared n. So I've already stated that, so I'm just restating that. So basically, we've re-standardized using mu1 instead of mu0. Okay? So basically, I first subtract mu1 from both sides. Notice I no longer need the given mu equal mu1 part because I'm using that inside. Then I need to divide both sides by sigma over squared n. So now the left-hand side of the inequality is a z statistic, okay, because it really is centered at mu1. And then the right-hand side we can reduce to z alpha because it has a sigma squared in both pieces, so that cancels out. And then we get a minus mu1 over minus mu0 divided by the sigma squared in. So we reduce that all the way down. So if I wanted to know what is the power at a specific mu1, I plug all those numbers in, look it up on a z-table, and I can find the power. Okay? Now, that's not what we're trying to do. We're trying to find the sample size. So what we do is we fix a given power, okay, and then we'll find the sample size. So before we go to that, let's take a look at the pictures just to get an idea of what power is. So under the null hypothesis, which is a blue curve, okay, then we reject when we're right of z alpha. Okay, and that basically is the type 1 error, the alpha value on the right-hand side. Okay, so the three big bold blue lines, that area represents alpha, type 1 error. Now, regardless whether H1 is true or H0 is true, right, I still reject the null hypothesis z is bigger than z alpha. So therefore, I said the same line at z alpha, and to the right of that now is the power value, because I'm now the right-hand curve, the red curve, is under the alternative hypothesis. Okay? So either way, we're okay. So in a similar manner, we can show that if mu is less than mu0, we basically get the same general equation with a less than inequality and a negative on z alpha to represent the left side of the curve. And if we do a not equal to, we basically get the two individual pieces, the same looking pieces with alpha over 2's in them for the two-sided case. So we can actually do all those, but we're only going to focus on the greater than case. So for a desired value of P1, so if I pick P1, instead of solving the power and getting the answer, if I give the answer to P1, then since I know alpha, and I know mu1, and I know mu0, and I know sigma, I can solve for n. Okay, so it becomes an algebra problem to rearrange the equation for a given P1 and so again, let's go back to our greater than hypothesis where the power is represented like that. And so given us desired P1, I want to find it such that I get at least that probability, okay? At least that power. So no, I really can't achieve the exact power of P1, although we can write it down. It would be if that inside part, right, because if z is greater than z that cuts off P1, right, so if the probability that z is bigger than z of P1 is P1, I mean, just like z bigger than z alpha is alpha, right? However, that's perfectly fine, but the problem is, since n has to be an integer, there's no way you're going to get exactly z of P1. You're not going to get the exact value that cuts off, say, 90%, okay? All right, so what we do instead is we find the smallest n that satisfies being less than or equal to zp1, because if your value is less than zp1, then the probability to the right of that will be bigger than p1, okay, for the greater than case, okay? So that's what we're trying to solve there. So we know alpha, we know mu1, we know mu0, we know sigma, and we could find z of P1 given a P1. So therefore, everything is there except n, we know. So, forming the algebra, so you don't have to do that, we rearrange all that and solve for n. We get z alpha minus z of P1 times sigma over that difference between the two means, or the size of the shift. That whole quantity squared gives us the sample size necessary. So if we look at an example, let's suppose the standard deviation is 4, and mu is equal to 10 is the null hypothesis. We want to find the required sample size that if mu shifts to 14, okay, so moves up by 4 units, with power 90%, then, and an alpha of 0.05, okay? So again, that's giving us the z of 0.05, the z of 0.9, mu1 is 14, mu0 is 10, and sigma is 4. So we know everything in that equation, okay? So z of 0.05 is 1.64, as we've seen. Z of 90% cuts off 90 to the right. Will have to be a negative number, right? Because it's cutting off more than 50% to the right of it. So that's 1.28. So put the 4 in, put the 14 10, solve it all out, we get 8.53. because n has to be an integer, we write that equation as a greater than or equal to so that you always round up to the next integer. So we need at least 9. Therefore, 9 will give us slightly more than 90% power. Okay? All right, so now what if the standard deviation is unknown? Then we use S as our estimate of sigma, and we no longer have a normal distribution. Okay? So instead, we have a t-distribution if we don't know the standard deviation. Well, this is a problem, because the t-distribution, we need then in the same basic equation as the z, we need to replace z alpha and z of p1 with t alpha and t of p1. But the problem is, both t alpha and t of p1 depend on degrees of freedom, which involve n. So therefore, we're trying to solve for n. We don't know n, and yet the formula involves n in the degrees of freedom. So this is a problem. So therefore, it becomes an iterative approach. We can write it as, is n bigger than? And all I've done there is I've substituted S for sigma, and the T alpha and TP1 for Z alpha and ZP1. So basically, you start with n equal 2. Therefore, you're looking at a T alpha of 1 degree of freedom and a T of P1 at 1 degree of freedom. Say, is that equation a true statement? If not, then I move to n equal 3 and n equal 4, and so on. All right, so suppose the estimated standard deviation is 1. So S is 1. We have mu0 is equal to 20. Okay, the mu is equal to 20. And the mu1 equal to 22. We're looking for 80% power, again using 0.05. So first of all, let's just reduce our formula with what we know. So we can plug in the 1 for S, and the 22 minus 20, or 2, as the difference in the bottom. So basically, it reduces to a simple formula as T alpha minus T of P1 over 2 quantity squared. We start with n equal 2. So is 2 bigger than 6.313 is our T alpha. T of P1 is actually negative. I've just sort of minus a negative. It's going to be a plus. 1.37 divided by 2 all squared is 14.78. So 2 is not bigger than 14.78. Okay? So the answer is no. What about 3? Is 3 bigger than 2.91 plus 1.06? Again, the 1.06 is negative, but it's minus a negative, so it becomes plus. 3.96. So 3 is not bigger than 3.96. Then we move to 4. And you see that 4 is bigger than 2.77, okay, the required number coming out. So the sample size is 4. Okay? In general, you should be using software to do this. You don't want to be doing this. I chose the numbers in this particular example to come out with a nice small sample size like 4. Okay? If it comes out with something like 15, it's going to take a while to walk through all that. So you really want to use software to do this. Now, what if there's no good estimate of the standard deviation at all? Okay? So I don't even know S. I don't know anything. Don't know S, don't know sigma. So notice that the sample size depends on the difference, mu1 minus mu0, not the actual values of the two means. It really doesn't matter whether we're talking about 22 and 20 or 4 and 2. It's really that difference that's important. Okay, so you're talking about a shift of 2. So we can exploit this fact by redefining the difference in standard deviation units instead of units of the problem. So instead of picking the 22, okay, what we can do is say, well, what if we shift 1.5 standard deviations? Now, I don't know what that's going to be. It might be 22, might be 26, might be 21. I don't know because I don't know S. Well, but I know if I shift 1.5 standard deviations from my target, I probably should stop that and figure out what's wrong. I'm just using 1.5 as an example. We could use any number of standard deviations that we want. So what happens then? Well, we take our formula and we replace the mu1 minus mu0 with 1.5s, okay? And then there's an s in the top and an s in the bottom, which we don't know, but they cancel each other out now. So now basically we reduce our formula to T alpha TP1 divided by 1.5, okay? Or whatever number of standard deviations that you wanted to pick up, okay? All right, so is that okay? So notice that the last example would be 2, all right? Was a 2 before. It was really 2 standard deviations, okay? If you do the iterations, you would find that the answer to this problem is actually 5. So I'll leave that to you if you would like to try that, to do the same kind of idea that I walked through. Notice on those T alpha and TP1, there is n minus 1 degrees of freedom. I just did not write it there. But if you walk through the same iterations, you should come up with 5 being the first one that solves that. All right, recall that the paired t-test actually reduces to the one sample t-test. So the calculations then would be identical here. We're just using mu0 of 0 instead of a mu0 of 20 or 30 or 60 or whatever it might be. So really, doing a paired t-test is identical to what we just did. Similar calculations, assuming equal sample size, can be done with like the 2 sample t-test. And we need equal sample size, as you could probably imagine there, because otherwise your formula is going to have an n1 and an n2 in there, and how do you solve for that? So if you assume it's the same n, then you can pull it out and just solve for n. Okay, otherwise you got too many unknowns. Okay, so we need to do that, or not necessarily equal, but some ratio. Maybe we say n1 is equal to 2 times n2. Then we can solve that too, as long as we can solve it down to a problem that only involves a single n, whether they're equal or some ratio. Also, assuming that the required sample size will make a good approximation to the normal distribution, then the power formula using z can be modified to handle the one proportion problem. So basically, we're just replacing sigma values with theta 0 type values, and we can follow the same general z type statistic. And finally, assuming equal sample sizes, we could also do a 2 proportion test as well. So all those valued things can be done using the same general thing. I'm not going to go over how to do those, but you can just adapt the same things, same process, just moving in different substitutions. Now, shifting gears a second here, another approach for sample size is just to look at it from a confidence interval point of view instead of the power point of view. So what if I want to use a confidence interval and say that I want my estimate of the true mean to be within some bounds? So suppose I don't have a target at all, but I'm going to go out and collect some data, and I want to estimate mu, the true mean, within some reasonable range. So I would use a confidence interval to estimate the mean, and I want that range, the width of that confidence interval, to be no bigger than b. Okay, so I got 2b, b plus or minus b on each side. So I want to be within that distance. All right, so again, let's just start by assuming we know sigma. So if I do that, then the confidence interval for mu is y bar plus or minus z alpha over 2 sigma over the square root of n. And what I'm saying is that the z sigma over square root of n, which determines the width, right, how big that is, plus or minus, that needs to be less than or equal to b. If I make that whole thing less than or equal to b, then I know that my confidence interval will have that, will be within plus or minus b of the true value. Okay, so again, if for a given b, I know z alpha over 2 and I know sigma, so therefore I can solve for n. If you perform that, a little bit simpler algebra here, we come up with z alpha over 2 times sigma divided by b whole quantity squared, where again we would round to the next integer to solve that problem. Okay, so this is another approach instead of power. So let's just do an example. Suppose we require a sample size such that we're within plus or minus 0.5 grams of the true mean. Okay, so I want to be really tight around that true mean. 95% confidence, assuming that the standard deviation is known to be 1.65 grams. So plugging that in, the 95%, the alpha over 2 gives me 1.96. The 1.65 is sigma, and 0.5 is b. Plug all that in, square, I get 41.83. Rounding it up means I need at least 42. I could use the same general iterative approach that can be applied to the bound on a confidence interval for t. Okay, so if I was using s instead, again, I could put the t in, and then I'd have to do that iterative approach as well, because I don't know what the t alpha over 2 value is. This is the common approach for proportion data, this confidence interval approach. It's common for proportion data in cases where there's no hypothesis, especially true in surveys. Because in surveys, we don't have targets for things. We're just asking questions, and then we want our estimates of the true portion of the bound. You'll see this written in papers or journals or newspapers where they'll say the margin of error is plus or minus a certain percent. Well, what we want to do is we want to fix what that margin error is going to be beforehand. So what we want to do is choose a sample size that does that. So we don't have a hypothesis for it. We don't know what the percentage of people are going to believe a certain thing. We just want to make sure that we're getting enough samples to get within a certain bound on that. So a confidence interval for P is P hat plus or minus the alpha square root of P hat 1 minus P hat over N. That's the confidence interval. So again, if I work that around and solve it for N, I get P hat 1 minus P hat over that. Now this is similar to that value being like sigma squared, okay, from the mu one. So if I knew sigma, then I stuck it in, and it was no problem. Same here. If I have a good guess of what P hat's going to come out to be, like I know the question they're going to give me roughly 90% of people are going to answer a certain way, then I could use it. Otherwise, what's common to use is 0.5, because 0.5 times 0.5, which is 1 minus itself, is the maximum you can get of any two values that are complements of each other within the 0, 1 space. So for example, 0.9 times 0.1 is lower than 0.5 times 0.5. So if you can see that, looking at that formula, if I use 0.5, I'm maximizing it. In other words, I will use an n that is the maximum I could ever need. I know that I've taken enough data guaranteed to be within the bound, no matter what the real P hat comes out to be. So it's sort of worst case scenario. So a lot of people just use P.5 in there. So basically you get a 0.25 times your Z alpha over B squared kind of quantity there. Okay? So this confidence approach is pretty common for this kind of forcing data especially.